in the previous video, I mentioned this thing right here, and I wasn't sure why x is bigger than xp as when p is less than 1. And the x is also positive. Now, and then after the video, I immediately thought, well, the reason is simply because you need to, anytime you compare something with some kind of a power, the first thing you do is slap the natural log on it and see what happens. So when you do, then you get this equation. The natural log of x, which is positive, is going to be bigger than that same number multiplied by a number that's less than 1. Is that, is that simple? Still, I wish your book had mentioned this line. That would have helped. But either way, the solution is direct. I mean, directly available. So let's look at the, the homework. Okay. First one, I want to talk about problem 349, which is a direct application of Rule 15 in the appendix. Appendix on page 700, where the integral of a squared minus x squared, in this case a equal to 2, is simply the inverse sine, also called arc sine, the inverse sine of x over 2, and you apply it from 0, which is just 0, and then you let t approach 2, which is just 1, right? And then sine inverse of 1 is pi over 2, and you're done with this, piece of cake, right? And then, so next, let's look at problem 351. So problem 351, we're integrating x e to the power minus x from 1 to infinity. And to do that, we are going to apply Rule 42, which is a direct application what to do when you have x to the power n times e to the minus x. Or you can use integration by parts, letting u equal to x and dv equals to e to the power minus x dx. That works very fast as well. One is no better than the other because that's one of the easier integration by parts to do. But anyway, either way, so however you integrate this thing, we're going to integrate it, okay? And then so you have the integrand, and you're going to evaluate it from 1 to t, and while t is going to infinity. To do that, however, you are going to be stuck with the L'Hopital's rule, okay? You have a situation where you have a t on top and t on the bottom or something, and then they both go to infinity. So you have the infinity over infinity situation, for which you are allowed to apply the L'Hopital's rule, which means you take the derivative of the top and the bottom. Now remember, the L'Hopital's rule only works if it's infinity over infinity or 0 over 0. Any other situation do not work. Okay, so you apply the L'Hopital's rule and you prove something and get the answer. What's the answer? Yeah, the answer is right here. When you plug everything in, and it does converge, and everything works out nicely. So that's problem 351. Next, let's look at problem 353, where we're integrating x to the power cubed. And that is, with that, we're going to use the comparison theorem, because integrating 1 over square root of x to the power cubed might not be a simple matter. Okay, so we'll figure out an easier way to do it by finding something else that does work, and with that, we're going to prove it one way or the other. So to do that, what are we going to do? So I made a couple of attempts. First, I attempted to compare it to, this is x cubed. Okay, the problem is x cubed. I guess somehow I decided never mind what I decided to compare. It didn't work. Okay, so let's look somewhere else where I did decide to compare it to something. What did I compare it to? Give me a second. I can't even read my own stuff. Okay, I figured out what I was doing. Now, here's the original problem, and we're gonna say that this one, being the +1 is what down there is what's causing problems with integration. So why don't we just let's see down here, right? We will let me move it over a little bit. Okay, so why don't we just right here, like, just get rid of the plus 1 and say that the original integral is going to be less than this one, okay? Because the denominator up here is bigger, so then the overall fraction is going to be smaller than this, okay? Being that it's smaller, we can, which I also wrote down right here, okay, it's smaller. Now, being that it's smaller, then we rewrite it this way, and we can just go ahead and integrate this thing and see where it goes when t goes to infinity. So we integrate that, it becomes this thing, and then everything pops out, and it turns out it converges into 1/2, and therefore the answer is convergent. And being that that's convergent, then it's bigger than something else that's also positive, and so that one is convergent as well. Next, let's look at problem 355, where we integrate e minus x cosine x from 0 to positive infinity. To do this one, to do this integration, when you look at it, the first thing you might want to try is integration by parts, right? Which is what I did right here. Now let's look at the integration by parts. Remember that cute rule that your book provided, LIATE, which means you do the, in here, in our case, you will do the algebraic, in here you will do the trigonometric, okay? U will be the trigonometric before exponential. So we'll let u equal to cosine x and etc. And then I got to this part, applying the integration by parts, where we get, we ended up with something with sine x, almost identical, except that now there's sine x. So at that point, I was worn out. Okay, I wasn't going to do integration by parts anymore. So I flipped to the back of the page and pulled out Rule 45, which gives a direct answer to this type of problem. And I copied it down with a equal to -1 and b equal to 1 in the formula. And so then I copied down the answer directly. Okay, plugged it right out. And then let things going from 0 to t goes to infinity. When t is infinity, e to the minus x goes to 0, okay? And then cosine x and sine x goes, those two things are at most 1 and -1. So when they add it together, the most they can be, and they might not ever be that much, is 2 and -2. So that's limited, whereas e is just taking a dive to 0. So whether it multiplied by 2 or -2 or not makes no difference. It's still going to 0. So at that point, we will say that then as t approaches 0, the limit goes to 0, and then subtract it when e equals 0. That's some kind of value you can evaluate, and then the final answer is that the integral equals to 1/2, and that's the answer. All right. Next, let's look at problem 357, where we're supposed to integrate from 0 to 1 of natural log of x over the square root of x. Now, to do that, I decided to do integration by parts, following that liat symbol before, where the log is takes first choice. Okay, so I let u equal to the natural log of x, and du equal to the rest of it. And then we work through the process of integration by parts. If you are rusty about it already, no problem. Just go back to the section in chapter 3 or something and refresh your memory on how to do this type of thing. So then I come up with something like this, which is good, right? Because the second part, mostly the second part, the integral, this one over here, is very easy to do. So I did it. And then the first part then start causing a problem, because there's a infinity over infinity situation happening, which means that, I guess, yeah. Well, I think it might have been infinity times 0 over here. So I pushed the square root of x, which is t now. Push t down to the bottom so that it becomes infinity over infinity with a negative sign. And then I applied the L'Hopital's rule. And everything came out okay. Okay, the first part just ended up being 0, and the second part being 4, and the answer is -4, which is correct. Next, let's do problem number 359, where we're supposed to integrate over the entire number line, okay, from minus infinity all the way to positive infinity. In that case, we are going to do as the book instructed, which is to cut the problem by half, probably break it at 0, and then have two integrals, one going from minus infinity all the way to 0, and then the other one goes from 0 all the way to positive infinity. So once we have broken our problem into two chunks, in my case, I looked at it and realized this problem, this 1 over x squared plus 1, is an even function. That is identical on both sides of the y-axis. Now, if you don't see that or don't remember how that works, just plot this graph on the Desmos graphics calculator, and you see it right away. I think it looks, like an infinite mountain. It goes up a little bit and then go back down again. But whatever it looks like is not that important. Then my point is, I'm positive that being an even function, we just have to calculate it 2 times. Like it goes from 0 to infinity. If that converges, it exists. If it doesn't converge, it's a goner. So then, and then another thing, so that's what I'm going to do. And then another thing I want to talk about is example 3.48, where we already did that this particular improper integral. I guess I wrote it down here. I guess we need this thing, right? This particular integral is equal to 1. And, well, being that, well, maybe we don't need that information. But anyway, do we need the information? Well, maybe. Yeah, I think so. So, because we're only comparing here, we don't have to necessarily calculate what this thing is. And so, being that we know that, we also know that this fraction, whose denominator is slightly bigger, means the fraction itself is slightly smaller than this thing, which means that, give me a second. Why do I have so many of them? Oh, when I was comparing this function, the 1 over x plus 1, when I was comparing it to 1 over x, there should be some detail that I forgot to mention, is that 1 over x in the example only goes from 1 to infinity, whereas this thing goes from, from the entire number line. So to compare them properly, they are equal to 2 of 0 to infinity due to the function being symmetrical from on the negative and positive side of the x-axis. However, to reasonably compare, I have to break it down to going from 0 to 1, okay, and then the other one is from 1 to infinity. That way I can compare it with this one in a fair comparison. Otherwise, this has extra stuff. So, but this one is already, we know this one works because there's no problem here. The only thing that might not work is this one. And then, so in comparison, then we know, comparing with this example, being that it's smaller, and this example converges, so then we know this part converges. And this is a bit of an extra work because in reality, we don't really care, right? Because in reality, we just need to calculate what this value is. So here, so I did that here. This is a standard formula, which is rule 16 on page 700. When you pull that out, it means the integral of this thing is simply tangent inverse. So you plug tangent inverse in there. And then there's 2, don't forget there's 2 of them. And then, yeah. And then letting t go from 0 to t equal to 0. And then t goes to infinity. When t goes to infinity, tangent inverse goes to pi over 2. So 2 of them becomes pi. Now, if you're not familiar with the tangent inverse function, please plot it somewhere and take a good look at it. It approaches as x. The tangent inverse function approaches pi over 2 on positive side and negative pi over 2 on the negative side. So that's that. Now, next let's look at problem 361. Give me a second here. So the next problem we're going to look at, problem 361, it has, you go from minus 2 to 2 of integral of 1 over x plus 1 squared. Now that's a fairly standard looking integral with a slight problem of what to do when x is minus 1, okay? Because then the denominator is 0, and then we're going to have a problem. So, and then of course they want you to integrate from -2 to 2, so that -1 is nicely included in our range, in our domain for the integration. So we are going to have to break it into 2 chunks as the rules require. When that happens, then you will integrate the first part from -2 to -1, right, where it reached the denominator is 0, and then do the second part from -1 to 2. And to do that, then we are going to, but first, do a quick u substitution. To make things easier, we will let u equal to x plus 1. And then we'll arrange all the endpoints. When x is -2, then u has to be -1, and so on. And then, so the integral turns into this one, right? It integrates from -1 to 3. And, okay, then what? If it's -1 to 3, then it becomes, the problem exists when u equals to 0. So we break up the integral into 2 parts, from -1 to 0, and then from 0 to 3. And then we'll integrate the first one, okay? I didn't even get to this. Well, yeah, we'll integrate the first one. It becomes u to the power -1 as t approaches 0. Yeah, that becomes infinity. So it goes to infinity, I mean. So it diverges. Therefore, this integral diverges, and we don't care what the rest of it does, okay? It's a goner. So next, let's look at now problem 363. Have you do the integral of sine, but going from 0 to infinity. Now that one, we know that it diverges, and here the reason is because we know what sine does, right? Sine does this going up. Oops. Sine does this going up and down thing. It just keeps doing that. So its integration as x moves across the x-axis, it'll go up to the integral becomes, I don't know, 1 or something. You know, it becomes positive, and then it becomes negative. So at this point it'll be 0, and then it just keeps doing that. It goes 1 or something. I don't remember what it is, 1, 2, something like that. But anyway, it'll go up. The value of the integral will drop down to 0, and then it just keeps doing that. In fact, yeah, the integral of sine is the antiderivative of the sine is the cosine. So its value goes up and down from 1 to -1, and it doesn't ever stop doing that. So it's not converging. It's not going to infinity, but we are still calling it diverge. Okay, anything that doesn't converge is automatically diverge. So the answer of this one is that it diverges. All right. Next, problem 365, where the book throws you an easy problem so that you can relax a little bit. Okay, so then the easy problem just says we're integrating from 0 to 1 of 1 over the cubic root of x. That is, well, x is not defined as 0, but that doesn't matter, because when you do the integration and do the power rule, then everything comes out nicely, okay? Because then x goes on top, and then when it goes to 0, it's just 0 or something, and then everything comes out nicely. So that's that. Now problem 373, another quick problem where you have to integrate this thing from 1 to infinity. So you just perform the power rule integration where x goes on top. So when t goes to infinity, well, so does x. So the whole thing goes to infinity and diverges. And that's about it, right? Next, let's look at problem 383, where we have the situation of going from -infinity to infinity of x over x squared plus 1 squared. Now you notice that this function is an odd function on top, just x, and an even function on the bottom. And when you have an odd function on top and even function on the bottom, you end up having an odd function. It's just a point that is not necessary to know this. I just want to mention it. So in that case, we are going to do a basic u substitution where we let u equal to the denominator, just the part where before the squared. That is, we'll let u equal to x squared plus 1. So if u equal to x squared plus 1, then du is 2x dx. And then we have to adjust the limits, the top and the bottom limit. Whereas where x is 0, when x equals to 0, then u equals to 1, calculating from here. And then when x approach positive infinity, you will also approach positive infinity. Also, furthermore, if x approach negative infinity, you still approach positive infinity. Okay, and the reason we have to do that is because we're going to have to break this thing into two chunks. You know, by the rule, you go from 0 to infinity and then from negative infinity to 0, 2 parts. And once you integrate it and plug the u in, the 2 parts end up looking the same. You know, you're both integrating 1 over u squared, which becomes u on this side, right? Becomes u minus 1 over this stuff. And then you calculate it, and the one will end up being 1/2, and the other one being down here minus 1/2. So the answer is 0, which so the answer converges and is equal to 0, which makes sense because this thing, as I mentioned earlier, this thing is an odd function. And this odd function, if it converges, then it has to be 0 because the two sides are the same except one is the negative of the other. So it makes sense that the answer is 0. Next, let's look at problem 389, where you have the natural log, where you're integrating from 0 to 4 of x natural log of 4x. Now, the catch here is, of course, that when x is 0, then the natural log goes to negative infinity. And then there might be a problem. However, we will work it out to see if it comes out. So look at the natural log. We have, to integrate this thing, we will apply integration by parts, okay? Which, at first I tried to apply rule 47, but it looked even, and that actually is more cumbersome because they didn't take care of the 4. There's a 4 there, and so I might as well just do integration by parts myself, okay? It'll go much better. So I did the integration by parts, and the answer quickly popped out into something, right? And then, so I got here. Now, the thing about getting here is that this part, you have a situation, remember x is going to 0, that's the part where, t approach 0 is what we're concerned with. As t approach 0, you have a 0 times negative infinity situation, right? Because natural log of 0 goes to negative infinity. So we're going to pull off the L'Hopital's rule by turning, well, this thing isn't a fraction. L'Hopital's rule requires fractions. So you're going to push the x squared down below the division line and turn it into x to the power minus 2, and then apply the L'Hopital's rule. And that will get you somewhere that eventually it becomes 0, okay? As x approaches 0, the whole thing turns into 0. So then you plug in the rest of it, and I ended up with this number, 8 natural log 16 minus 4, which normally you probably want to simplify a little bit, the natural log of 16, which is 2 to the power 4, and get that 4, put it in front, that sort of thing. But the answer in the back is also this, so I didn't bother to do any of that. And that's the right answer. So this thing converges to whatever that is, right? 8 natural log 16, etc. And that marks the end of this section.